Welcome for the fourth lecture on artificial intelligence in robotics course. And this lecture is dedicated to the information gathering, robotic information gathering, and in particular to robotic exploration. So let's start with the robotic exploration and what is the robotic information gathering. So we can imagine that we have different types of robots, maybe team of robots, and we aim to create a model of some phenomena using these mobile robots, maybe autonomous mobile robots that perform measurements, and in general can perform these measurements in dynamic and a priori unknown environment. So the robots needs to sense, needs to navigate, needs to localize in the environment and create a model of the spatial temporal phenomena. So the robots also needs to determine where to go and what should be the next action to actually improve the model of the phenomena. And there are multiple challenges in robotic information gathering. The first is how we can improve the phenomena model, where we need to take new measurements. And with this bunch of possible locations, we also need to decide where to go first. So, and we need this in runtime and during the online, and so we need to make the decisions maybe in situ using onboard computational requirements. And of course there is the question how to efficiently utilize robots. We have a bunch of robots. What will be the benefit of using 1, 2, maybe 4? How we can exploit the team of robots? And of course, there is the fundamental problem of mobile robotics, and that's the navigation. How the robots will reach the selected locations. And of course, there is the trade-off because if the robot will go to unknown environment, then it will improve probably the model. But if the robot will stay in already known environment, it may help it to improve the localization. So the robotic information gathering is combination of learning. So we learn the environment, we learn the model, and we need to adapt to the model. And of course there are let's say two main sources of uncertainty. Of course there is the uncertainty in sensing, because sensors are not precise, and also if we decide and plan some action, of course there is also uncertainty also related to the model, precise model we have. And also how once we perform the planned actions, then it is always not perfect. And the main challenge is that we need to address all these aspects together, probably in a cost-efficient solution and in situ decisions, so that we may not rely on existing communication to some cloud service or so in general. So what is the robotic information gathering? And it's also related to multi-go planning, which will be covered in the next lecture. So in robotic information gathering, we basically aim to determine optimal solutions to collect the most relevant, the most valuable measurements in a cost-efficient way. It can build on very simple path planning. We showed some in the previous lecture, or trajectory planning, and we can rely on point-to-point planning. But we may also have a bunch of locations to be visited, and then we can address the optimization problem, combinatorial optimization problem. What will be the order of visiting these locations? So we aim to determine the sequence of locations to be visited. And of course there is the general point of view depending on the task and mission. They include the online decision making. There is the informative path or motion planning or persistent monitoring, which we will cover in the next slides. And there is a large part of the robotic exploration topic where we basically aim to create a map of the environment, usually as quickly as possible. But there are some other notion of the performance indicator. So what we also need is that during the determination of the plan, we need to satisfy, or we assume some assumptions, and we need to satisfy the constraints in the way that the plan we prepare is executable on the robot, so it's feasible for the robot. And related to the planning, we will cover the inspection planning and surveillance planning, and basically all these types of planning tasks can be considered as data collection planning, and we will have a dedicated lecture on that. And in both cases, and also in robotic exploration, as we will cover in this lecture, we can consider multi-go path planning. So we consider not only visiting one location, but maybe a couple of locations that may improve and actually is improving the performance of particular mission. Let's start with very general problem formulation, so informative motion planning, and we can consider robotic information as in general as a variant of the informative motion planning problem, where we actually aim to determine a trajectory, let's say like this P star, that is from all possible trajectories the one with the most informative information gathered along the trajectory. So it's the trajectory which will provide us the most relevant data. And of course we can have some constraints, and in this constraint there can be the budget. So we can imagine that from all possible trajectories, okay, so we consider this like this, our argument of maximum, and from that we will select that. But of course this is very demanding, and we can imagine that the trajectory is actually the action, so we are selecting the action that will provide us the most valuable data. But of course that's in general it's very complex and demanding, and we can discretize the problem and use comparator optimization techniques, but usually these scales poorly with the problem size. The trajectory is usually from a continuous domain, so we can sample the continuous domain, and that's related to sampling-based motion planning techniques, as did Geoff in this paper. And we will cover the sampling-based motion planning in the next lecture. So, and once you will have this notion and technique, you can apply it to generate trajectories and assess the trajectories, the information you can gather. And we will use the very similar idea also in these exploration approaches we will cover in this lecture. So a special case, let's say, of the robotic information gathering is persistent monitoring, which is that it's not one-shot mission, so you send the robot, you collect the data, and that's it. The persistent monitoring, it's usually related to the monitoring of spatial temporal phenomena. So you need to repeatedly visit the locations to deploy the robots in the environment to collect the data, because the model is evolving in time. And such an example is shown here, where we have multiple locations where we actually measure the wind to capture some spreading of some gas in the environment, or the pollution and so on. So you can use the search for next location to improve the model. We can consider the locations can be found as optimal sampling design, which is a problem to determine the locations to be visited. There is also a connection to the trajectory and planning, maybe motion and path and motion planning. And of course, if you have multiple locations, there is always the question of multi-goal path planning or multi-goal motion planning for the optimal sequence, because in reasoning in a longer horizon can save the cost the solution cost. And of course, you can further consider other constraints like kinematic or kinodynamic constraint. Of course, the path should be collision free. And in general, the problem is very challenging, and we need to consider the most important and relevant constraints and solve or address the problem under particular assumptions. So it's also related to what we captured in the second lecture about this frame problem. So the robotic exploration of unknown environment is or can be considered as a fundamental problem of robotic information gathering. The problem is to efficiently utilize in general a group of robots to create a map of an unknown environment autonomously. As you can see here, the robots are operating fully autonomously to create a map of this artificial environment in a gym at Charles Square. So campus. So the performance indicators can be like time to create, the map quality, also the energy spent, and we also have the constraints. We can have a constraint on number of robots available of the communication. So the performance in a real mission depends on online decision making, because there are these sources of uncertainty, and it's not sure where the robots will perfectly follow the plan. So it's necessary to consider the data collected and in situ decision making. So we also need to address the map building, determination of navigation waypoints, where to go next, coordination of action, path planning, and navigation to the waypoints. And we will partially cover this in the following slides. So the mobile robot exploration as a problem of creating a map of the environment is in robotics usually addressed or can be addressed by a fundamental approach, which is a frontier-based approach, and you can see the frontiers here. It's the red cells, and basically the idea is that we can navigate, or we can explore the environment once the robot is navigated to these frontiers, which is a boundary between the known white space and unknown, the gray color space. So this is related to also to the environment representation, and mostly we can use in such a setup a occupancy grid. We can also rely on availability of the laser scanner, because in the 2D environment it provides a great data. Of course, there is the next best view. So once we will select, we will navigate, then we will navigate to the next best view location. So time to create a map of the whole environment is one of the performance indicator we can use, and especially in a search and rescue mission. But it's related to what is the objective. If you like to create a map or you are creating a map to actually search for something, and we will cover that in the very last part of the lecture. What are the environment representation used in robotics? So first, let's imagine that we have a range measurements, or we have some sensor measurements, and we can use these measurements to build a map of the environment. And the robot can integrate these sensor measurements into a globally consistent map once it is localized. So we need some localization. And in many cases, we cannot rely on GPS. For example, indoor doesn't work. And there is a huge topic in robotics which is called simultaneous localization and mapping, also abbreviated as SLAM. And in this approach, the robot actually used the map being built to localize itself. And I would like to highlight that this map is primarily to help to localize the robot. It is a side of product of the SLAM, even though we can use it for other purposes. But the SLAM can use different types of features, different types of map, and they may not be very useful for the purpose for like the exploration. And to show some the example of how this is working, you can see this animation where the black dots represent the map, the blue dots or the path is the trajectory of the robot, and the red dots is an actual scan from the 2D laser scanner, and the robot tries to find the best fitting transformation of this scan to the previously mapped points, and it actually estimates its movement, and once it is done, it can integrate the new sensor to the map. And just to know that these red scans are artificially adjusted to highlight the effect of the finding the transformation. In this case, it is an iterative closest point. It is one of the simultaneous and localization mapping technique. So in this case, we are creating a point map which is suitable for localization, but maybe not suitable for like exploration and planning. So you already have notion of the planning in the grid. So let's construct from this point map a grid map where each cell represents this obstacle or free, and we have the notion of occupancy grid map, where each cell is a random variable that models the cell is occupied or not. So for the occupancy grid, we have a couple of assumptions, and one of them is that the area of a cell is either completely free or occupied. Okay, so that's of course depends on the resolution. There is also another assumption that is that cells, random variables, are independent of each other, and the state is static. So, and this is actually quite interesting because this helps a lot. But if you think that you have some object, you have like table or some other like box in the environment, there is a occupied cell, and the neighborhood cell of this table should also it's likely to be occupied if this cell is part of the table. So in reality, it is probably not always satisfied that these random variables are independent of each other, but we don't have any priors on that, so we can consider that they are independent. So a cell is a binary random variable modeling the occupancy of the cell, so it's a probability the cell Mi is occupied, and there is surely obstacle if it is 1, and it is surely free, it is 0, and maybe you can set up in the middle, we don't know. So we have the probability distribution of the map, and what we are actually doing when we take a measurement, we actually provide the estimation of the map from the sensor data and the robot poses. So we have a position of the robot and we have new sensor data. So these are the conditional probabilities. And you should remember your bias rule and Markov process assumption. Okay, so and we will use it. So binary bias filter, just to remind, because it's probably covered in other courses. So we have sensor data, and which is in time sequence, and we have the robot poses, it's also time sequence, but binary random variables are independent and states are static. So we can use the previous states, and which is the Markov rule. And we have the bias rule for the conditional probability, so we can massage the equations, and we can got the probability a cell is occupied as this expression, or probability a cell is not occupied in this expression. So we can consider the ratio of these probabilities, and we can again massage the formula a bit, and we will have this is the sensor model. This is the recursive term, and this is the prior. So, and once we have this, we can also use the log odds ratio, definite as say information, logarithm of probability divided by 1 minus the probability. and you can consider from that the probability is this term. So we can set up the inverse sensor model, the recursive term, and the prior. So how or why we are doing that? Because now we have a model of the sensor, and we can have this occupancy grid map update. So for each cell and of the map, and for each cell in the perceptual field of the new measurements, we can actually update the model, the map, using this very intuitive formula. And why it's important? Because actually the occupancy grid mapping has been developed motivated by noisy sensors. So, and this is the inverse sensor model for sonars, the range sensor. So if we have a measurement, so we are quite sure about it here, but we are not sure about there is not like single beam. So it is something like that. So if we have a measurement, we have the notion, okay, this is most likely the free space, and this is probably the obstacle where the sound has been reflected in the sensor, in the sonar sensor, and so we can use that to actually cover or update the map, not like a single measurement, but considering the characteristics of the sensor. So we can consider the occupancy probability depending on the measured distance. So we particularly measure this, and we are quite sure this is free space, but again we are not completely sure. So we put some occupancy probability here, but we are quite sure that somewhere around the measured distance should be the obstacle. So we increase the obstacle, the occupancy probability. So, but usually nowadays we use the laser sensor, and the model is very sharp. It's very precise. So we are quite sure, much more sure than for the sonar, that it's free space and up to the measured distance, which is surely the obstacle, because the laser beam has been reflected. So we can consider, okay, this is the point, but in fact we measure by laser beam some surface, and it is reflected from in the direction of surface normal. Okay, but basically what we can do with this laser, very simple technique, that in our grid map we can actually raycast a line or straight line segment and update these cells. And for that, you can use the algorithm for drawing lines from the computational graphics. And this is basically the idea, but you will implement that on the labs for some of your homeworks. So what is actually quite interesting, and this is covered here and especially here, that if you consider that you are raycasting the beams, and you have very dense sensor, for example, you may update some of the cells more frequently. So it may influence actually the map and the model. So that's something, if you are interested, take a look to these references for more details. So in addition to 2D, we can consider elevation map, which is shown in this example from the tunnel circuit, or this is probably the Edgar mine, old gold mine, where the robot is navigated. And for passing the obstacles, we can actually rely the robot is always on the terrain, and we need to consider what is the elevation. So you can consider this 2.5D elevation map. And for example, in this approach, we actually consider a Kalman filter to update the elevation after each observation. So you will have this prior. So if you are familiar with the Kalman filter, you can just use this updates. But of course, there is also the way to consider this occupancy grid in a 3D. In 3D, it is more memory demanding, and usually there are large portion of free space, so we don't need to have a final resolution for very large volume of free space, and that's the reason why octrees data structures are used. And one of the viable data structure or technique is called Octomap. You can download it, and it's also part of the robot operating system. And you can use it, but there are also some drawbacks. But basically, it is a technique viable. And here you can see the example of the collected map from the DARPA Subterranean Challenge in an urban circuit scenario, which is unfinished nuclear power plant at Elma in Washington State. So if you are looking for more details, you can follow the link. But it's not only the, let's say, grid-based representations. There are also representations that are unbound by resolution, and they have different advantages. So one of them is normal distribution transform occupancy map. So it's based on normal distribution transform, which is actually the description of the obstacles using normal distribution. And in this case, you can consider, okay, this is the occupancy grid, and instead of occupancy, we actually model the occupancy probability. We model as a normal distribution. So it has a couple of advantages. It's actually quite robust, and we can also create from some dense representation, some low resolution map that may be sufficient for navigation of such vehicles. If you are familiar with the machine learning Gaussian processes technique, then it may also be used for model the occupancy or elevation as a function of position. And the Gaussian processes in theory will fill gaps between the measurements. What is the nice feature of Gaussian processes is that predicts a normal distribution and provides the description of prediction uncertainty, and we will use them in information theoretic based approaches. So some of the example is shown here, what we can render from that representation. So, and there is, let's say, a little bit more or less demanding, more convenient representation using Gaussian mixture models. It can be used to model the observed surfaces, and some of the examples, or the example is shown here. So if you are interested in other representation of the environment, you can follow these references that will provide you a good starting point. There is also this one is relatively new. Vani by Vani Tabib. So if we have a Gaussian process for modeling the spatial, but maybe not really the spatial, that we can consider that we are modeling some other phenomena. So we can consider the kriging in spatial modeling. So basically the kriging is a technique that once we have a notion of uncertainty of our data, of our model, or variance of the model, we can consider that the next we can diminish the uncertainty of the model if we take a measurement in the location with the highest uncertainty, the less certain data. So, and this is example of combined exploration with traversability assessment learning. So the robot is building a spatial map, but like geometrical map, but also consider that each particular cell is traversable or not, and measure or model this by using Gaussian processes. So at the beginning, the robot doesn't know anything about the environment. It models the traversability, and this is the variance of the model. So this is the uncertainty, and the robot is really unsure. So about like this wooden blocks, it's red, so it's going there. It thinks it is quite easy to traverse, but after a few steps, as you can see, the model will be updated. The robot realizes it is quite costly. It's now red. It is quite sure that it is costly, so it diminishes the variance. And the robot is actually navigating in combined form to not export environment part and the areas with high standard deviation or variance. Let's continue with a very fundamental approach to robotic exploration, and it is frontier-based exploration. And in frontier-based exploration, we have a grid, occupancy grid. And the basic idea is that the exploration is a navigation of mobile towards our unknown regions, and these unknown regions are characterized as these frontier cells, which is a border frontier between the known free space and unknown regions. So we have the occupancy grid, so we can establish this free states or classify each cell into three possible classes. There is a free space. If the probability is below, for example, 0.4, there is unknown, there is the obstacle. So once we have this grid map, we can use the grid-based path planning for that. And you can see the performance of some frontier-based exploration on this video. But basically, what we can do, or what we are doing, it is an iterative procedure where we run simultaneous localization and mapping in parallel on background. But for the exploration strategy, we have the map, so we have some initial scan, and we collect the reachable frontiers. And of course, at the beginning, there are none of them, so we update the occupancy map using new sensor data. Okay, that's running on background. We create a grid map from the map using the previously mentioned thresholding. We grow the obstacles according to the dimension of the robot to actually ensure that the robot is able to reach the locations. We determine the frontier cells in such a map, growth map. We filter out unreachable frontiers because it doesn't have a path from the current robot position. And for simplicity, we can choose the next best or the closest or nearest frontier. So we assess the frontiers using a path from the current robot position. So that's and once we have that, we can plan a path which can be a little bit different, maybe more detail, and navigate the robots towards the such a location or frontier. So that's basically, and we repeat it. And the question is when we will repeat and how frequently we will repeat. So what is the trigger for replanning? It can be that we reach the goal, or it can be after traveling a few meters, or after some few seconds, depending on the computational time and velocity of the robot. And so that was the basic idea, but of course you can improve this concept, mostly using the notion of utility function. And utility is what is the information you can acquire if you visit some location. And one of the way is that you can project, okay, if I put my robot or sensor here, I can see, or maybe I can see this part of unknown part, so I can compute the expected covered part. And for example, here there is a dual sampling, so you have these three edges, and you put some random locations here, and compute and select the best one, for example, like in this case, this one, and you assess the covered part. So that's one of the approach, how you can improve if properly tuned. The other approach, especially for the office-like environment, is that once the robot enters some of the room, it's good to export the whole room. So we can perform online identification of the rooms and explore the whole room by a single robot, which is especially suitable if you have multiple robots. You like to send the robots to different, not the same room. And there is also other approach that we can not consider this greedy, but we will have bunch of possible locations to visit to actually cover or collect information about the unknown environment, and we can put it to a longer planning horizon and solve it as a traveling salesman problem. And in addition to that, we don't need to actually consider each particular frontier cells as a single possible location, but we can consider these free edges like this. So we can identify these single connected components, and then we can determine a representative of these free edges. So let's talk about the TSP in exploration. So the basic variant is that we have this next best view. Okay, we have the closest. So if the robot is here and we have these free edges, and we consider this representative of these free edges, so we basically have these red dots or red disk as the possible navigation goals. So we will just collect the shortest path. We will compute the shortest path to these locations and determine the closest one. In this case, probably we will choose randomly. That's next best view, really greedy. In the TSP distance course, we actually have the very same scenario, but now we consider, okay, if we have this current knowledge and we like to cover the or explore the environment based on this knowledge, so we have this 5 or red disks as possible goals. We need to visit all of them, and we will visit them in the best possible order. So we solve the instance of TSP. Of course, there is it's not close path, but you can consider as a close. That's technical detail. And in this case, you will have the path like this, and it's quite surprisingly that considering this let's say longer planning horizon, this is non-myopic next best view, it provides faster exploration, overall improve the performance. Of course, that you can ask, okay, it is demanding. No, it is not demanding if you have just few locations, and that's actually the motivation why we consider these representatives or free edges, so we can identify these clusters as a single connected components, and instead of considering all possible cells of this free edge, we actually cover that. And the idea is that we have an omnidirectional laser scanner, so it covers something like this disk. So we can probably cover this by like putting the laser scanner here. So what we need is to determine what is the number of clusters here. So and Marek Kulik actually established this formula empirically, and it will provide us the representative of free edges. So we significantly reduce the number of locations, so we can solve it the TSP. It's pretty quick for that case, and you can further consider clustering using not like Euclidean distance, for example, in the k-means, but some transformation also considering the distance traveled from one location to another location, which you can find in this paper. And here is another example of using this representative of free edges. So We have basic notion of frontier-based exploration for single robot, but we can also address the exploration using a group of robots, and there can be uncoordinated approach. So basically each robot is a sole player. It's independent to explore the environment, follow, for example, the closest frontier. You can just deploy it and you will see what is happening. But most likely you also need to consider, okay, I need to avoid the other robots. It will not perform quite well depending on the initial conditions. So if you have an environment like this and you will put your robot one here and robot one here and robot one here, another robot here, so this one will explore this will explore this, and this will, so. But if you consider that the robots are put at very close locations, then you need to somehow coordinate their motion. And there are centralized approaches, and you can actually consider the exploration as a variant of task allocations, and there are different assignment strategies. And actually decentralized or centralized approaches are actually running on a single computer, but if you run it in a distributed fashion and you have available communication, you will have a distributed. So this is distributed. Can be done in a distributed way, and you need to exchange the data. On the other hand, there are decentralized approaches, and the two decentralized approaches actually are completely independent. They don't rely on the communication. If the communication exists, the exploring units can improve the performance by changing the information, the maps, and so on. But sometimes you can find in the literature that the distributed and decentralized approaches are mixed together. So the terminology is not fixed, and also depend on the Europe and other countries, especially also for the swarm. But that's out of this lecture. So we have, for simplicity, the centralized strategy. It is a task allocation, and you can see here probably two robots. Yeah, here. So it's again an iterative procedure. We have the occupancy grid, we create the navigation grid, we threshold the occupancy probability, we detect the frontiers, we select the goal candidates, for example, these free edges, representative of free edges, and then this is the task allocation. So we have a bunch of locations, we have a group of robots, and we are looking for the best assignment of the current goal candidates to the robots. So using the current map. Then we create a plan for each robot, and then we perform the plan. And we can plan up to some S-max operations. Then we replan. And we finish the exploration once there are no goal candidates, reachable locations. So that's basically what is happening here. What is the performance? There are a couple of things. This is very simplified overview of the algorithm, but there are a couple of parts. Actually, in each part, you can improve the performance. So how you determine the goals from the frontiers. What is how you plan, and how you assign, and how you navigate the robot, and when to replan. All these actually affects the performance of the exploration. So let's go through the exploration procedure in a little bit more detail. So we repeat to navigate the robots using the current plan. Maybe the plan is 0, so we are done. We collect the new measurements, and we can actually do that in parallel. We update the navigation map, and then we repeat this until the planning condition is met. So this is, let's say, the navigation. Then we determine the goal candidates using the current map. if there are some, we assign the goals, we plan, pass, and repeat. And we stop the robots if there is no goal, right? So that's pretty much the exploration procedure regarding the decision-making parts. And we now can focus on this task allocation, the assignment of goals. I'm not speaking about frontiers because there can be different approaches how to determine the goal candidates from the current map. And generally it's a task allocation problem. So what we can consider is really greedy assignment. We can, in random order, assign the closest goal candidate to particular robot. So once the closest is assigned, it's no longer considered for assignment of another robot. It is also somehow working. What you can also do is that you can consider this iterative assignment, and basically you have the robot one, and you can compute the distance of the robot to each goal location, right? And you can do that for all robots, and then you can order this according to the distance. There'll be like 1, 2, and so, and you will order that according to this distance, and then you will assign first robot, then you follow up once you reach another robot, and so on. And this can be actually performed in distributed manner using the broadcast of local eligibility. So, but once we are in the centralized approach, we have a Hungarian algorithm you're probably aware of. This is optimal solution of task allocation problem for a particular decision point, right? So it runs in cubic complexity, and you can download the implementation by Technics, who make it viable. And of course, in our case setup, we can have less goals than the number of robots, and also more goals than the number of robots. So we can consider dummy tasks for that, and we can solve it. And what is quite important that, okay, Hungarian algorithm is an optimal solution for task allocation problem, but we are just in one iteration of this exploration loop. And of course, you already know there is the TSP distance cost, so we can employ it in multiple traveling salesman problem scenario, which is MTSP assignment, and you can consider cluster first, road second, for example. So how it's working, so we have the goal candidates, so we cluster the goal candidates to M clusters. M clusters is a number of robots. So again, consider the k-means. For each robot, then we select the next goal using TSP distance cost. Okay, that's pretty straightforward. You can solve it and so on as a TSP. So take a look to this record of the experimental exploration using multiple robots in same initial conditions, same algorithm for goal determination. So it's a representative of these 3 edges. You can see, okay, this Hungarian algorithm looks like it's good. It covers almost all the part, but the MTSP is more systematic. It doesn't need to return. So in the overall, it is faster. And again, it depends if your performance indicator is, for example, play it again. For example, if you have the time and you consider this is the expected coverage. So this will be like full coverage. So you can ask, okay, maybe it's better for me to have something like this, or it's better for me to have something like this. Okay, it's always depends on the scenario, but basically using a longer horizon provides you the benefit that you don't need to to actually return, because this return cost is counted in the MTSP or DSP distance cost. For the last remark on multi-robot exploration, let me motivate you to existing very simple, very intuitive decentralized exploration strategy, which is called MinPos. It basically works as a ranking system. And what you can have, we have 3, or in this case 6 robots, but right now we have 3 robots. And if you consider nearest goal candidate for each robot completely independently, so these 2 robots will decide for this frontier. For this frontier, and this will choose this one. If we consider greedy assignment of goal candidates in the way that we use, for example, this iterative assignment, so we consider that there are other robots. So this one is closest to this one is probably closest to that one, but overall this one will provide a better way. But in this case, there is one more left, right? So, and how the MinPos is working is that for each goal, we actually rank it for each robot. So we compute, or we consider compute the rank considering the distance of other robots. So this robot can, if the robot has the information about the map and position of other robots and position of the frontiers, this robot can rank this. Okay, my distance to that is like this, the distance of this robot to that is that, and this will reach that. So this is a goal for which this robot is closer. Okay, so I will decide, and same for this. So it's more likely that these goals will be covered by this robot, and this goal will be covered by this robot. So this robot will decide to follow this location. And again, similarly in this setup. And it's very, very simple to compute and provide some additional benefits. And of course, in this setup or in this case example, we consider that all robots have full information. But if you imagine that just for now, this robot doesn't know about this area and only have the notion about this location and this robot. So it will perform the very same, because it doesn't know about this, but knows that this robot is closer to that, and the remaining is this one. And same for this robot. So if this robot doesn't have any notion about other parts of the environment, depending on if the robot has some frontier here or here or here, it will choose one of that, or maybe also. But if we introduce the information, communication, it will perform better. So that's in this sense, it is decentralized, because it is performing, let's say, quite well if you have the available information, but it also works if you don't have the information. And to summarize the exploration or frontier-based exploration, let's consider the other parts that may influence the decision making. So we already see that considering Hungarian algorithm as optimal task allocation may not necessarily provide a better solution than, for example, MTSP, longer horizon approach. We also actually have a relation how the robots are navigated, and it is in this goal candidate selection. So, and this is the example. So if we use for navigation, for example, vector field histogram approach, which basically is that the robot has like omnidirectional sensing, and it's navigated along the path, and if there are some obstacle nearby, it is sensed, and the robot is actually slowed down. And using this, you can consider that if the robot is navigated to some location, like in this room, and I will try to draw it. So this is the room, and the robot is here, and it is planned to visit this using shortest path, and because we put the frontier here, right? So the robot will have this direction, or it is even better if you have the situation like this. The robot follows, so and we will have frontier here, and the robot will be here, and we will not consider this frontier representative, so we will have this nearest frontier. The robot will follow the wall, which can be like wall following, but you always sense the obstacles, and if you use this and without other additional tuning, the robot will slow down. And that's one of the side effects, that actually the selection of the waypoint and also the navigation. So if you will navigate the robot like this or like this or like this, then the real velocity of the robot will be different, and that may significantly affect the real-time performance. So it's all about the simplification we made, but the exploration is challenging because because it needs to consider all of them in the final deployment. So even that you consider some simplification that makes sense, once you deploy them on the robot, and depending on the other parts like this navigation, then it may have a different performance.